Hello, this is Mr. Faribaugh, and today I'm going to be teaching you about significant figures. Let's start by taking a look at a measurement. On this ruler, every line is worth 1 centimeter. So we must estimate the final digit to the 10th place. In this case, I would estimate the length of this object as 2.4 centimeters. Therefore, this measurement would have exactly 2 significant figures, or 2 sig figs for short. Let's take a look at the same object but measured on a more precise ruler and see what happens to the number of sig figs. Now this object would be measured as somewhere between 2.4 centimeters and 2.5 centimeters. So by adding the estimated digit out to the 100th place, we might get a length of 2.45 centimeters. This measurement is more precise and has 3 sig figs. Now let's take a look at what would happen if the length of the object falls exactly on the line. Should we call this measurement 2.4 centimeters? No, in this case we must still add an estimated digit out to the 100th place. But if it falls exactly on the line, we simply add a 0. So the number 2.40 centimeters is more precise than merely 2.4. This measurement has 3 sig figs. In this example, we have an estimate of the number of people that are in the United States. 312 million people. We know that this measurement is not exact down to the last person. So how many sig figs should this number have? It has 3 sig figs, which means that the final 6 zeros in this number are not significant. In this example, from a swimming event back in 2008 during the Summer Olympics in Beijing, the difference between the gold medal and the silver medal was a mere 1/100th of a second. Both of these measurements, 50.58 and 50.59, have exactly 4 sig figs, but that final 1/100th of a second was very significant in this race. So what is a significant figure? It is a digit that has meaning in a measurement or calculation. And you should realize that a number or a measurement should have the same number of sig figs whether it is written in scientific notation or regular notation. Out of all of the digits 0 through 9, the numbers 1 through 9 will always be significant, and the number 0, it depends. Sometimes it is significant and sometimes it is not. Here are 3 examples of where zeros may happen to fall in a given measurement. They can occur at the beginning, leading zeros. The zeros can occur in the middle of a number, captive zeros, and the zeros can occur at the end, trailing zeros. According to the rules for significant figures, leading zeros are not significant. So all of the measurements in the first column would have exactly 1 sig fig because these leading zeros do not count. Captive zeros are considered to be significant. All of the measurements in the middle column have exactly 3 sig figs. Now trailing zeros, it depends. It depends on whether or not a decimal is present or absent, and we'll take a look at both examples. When there is no decimal point, the trailing zeros are not considered significant. So a measurement of 40, 500, or 80,000, all of these measurements would have only 1 sig fig. If you were to write 80,000 in scientific notation, it would still only have 1 sig fig, written as 8 times 10 to the 4th power. Now let's take a look at what happens when there is a decimal point. Now the trailing zeros are considered to be significant. 4.0 has 2 sig figs, 5.00 has 3 sig figs, and 800.0 has 4 sig figs. If we were to write 800.0 in scientific notation, it would have to contain 4 sig figs. So therefore, the number would be written as 8.000 times 10 to the second power. Here is a rule that will help you determine whether or not the numbers are significant or not. We have the Atlantic and the Pacific rule for determining sig figs. Okay, if a decimal is absent, we're going to start counting the sig figs on the right side of the number. A for absent, A for Atlantic. Consider the number 105,000. A decimal is absent, so we start counting on the Atlantic Ocean side. And if there are any zeros on that side, we skip over them. Once we get to a non-zero digit, we would count every single digit from that point on. Therefore, this measurement, 105,000, has exactly 3 sig figs. Now if a decimal is present, we start counting the sig figs on the Pacific Ocean side of the number. In this case, the number is 0.0050. Once we skip over the leading zeros on the left side of the number, and we come to a non-zero digit, we count every single digit from that point on. Therefore, this measurement has exactly 2 significant figures. Now I'd like to talk about what happens when there are calculations involving multiplying or dividing. If you have measurements and you have to round off your final answer to the proper number of sig figs, it's important to discuss how we do this. Step 1, we do the math. The multiplication or division is done on the calculator, and we don't round off our final answer. Then we look at which measurement has the fewest number of sig figs, and we round off our final answer so that it has the same number of sig figs as the measurement chosen in step 2. And by the way, as we talk about rounding off our answers, it is based on measurements, which are not the same as exact numbers. So if you had a calculation involving dozen, where 1 dozen equals 12, those are exact numbers, and you would not round off your final answer based on one significant figure. 1 inch equals 2.54 centimeters. 1 mole of carbon is equal to 12.0107 grams. These are all examples of known facts in either math or science, and these are exact numbers, which will have unlimited number of sig figs. They will not affect the way we round off our final answer. Alright, in this example we have an index card that is measured for its length and its width. 7.6 centimeters and 12.7 centimeters. We're going to calculate the area by multiplying length times width. So 7.6 times 12.7 is equal to 96.52 square centimeters. Now we take a look at which measurement has the fewest number of sig figs. In this case, since 7.6 has only 2 sig figs, then our answer must have only 2 sig figs. The number is 96.52. We look at the digit next to the 6 and decide that it is a 5. We're going to round up in this case. So the answer is not 96, but rather 97 square centimeters. In our next example, we are going to calculate the density of an object. The mass is 8.44 grams, and the volume is 19.65 milliliters. To calculate density, we divide mass divided by volume, and we get 0.4295165 grams per milliliter. Considering that the 8.44 grams has the fewest number of sig figs, then we must round off our answer to have exactly 3 sig figs. Since the leading 0 is not significant, we start with the 4, and then the 2, and then finally the 9. It must be rounded up because the next digit after the 9 is a 5, we round up that position. So our final answer, when rounded, is not going to be 0.429, but rather 0.430 grams per milliliter. Well, hopefully this video helped you to understand what exactly significant figures are, how to calculate the number of significant figures in a given measurement, and how to round off your final answer in a calculation that involves multiplying and dividing. Thanks very much for watching.